We're going to do a lesson today on rational functions. This is our next unit. Just a reminder, you will write a test on polynomials on a Friday in class. Just make sure you prepare for that by doing some of the questions in the back of that multiple choice booklet. And if we finish this lesson early, you can continue with some of those examples. So basically, when I say the word rational, you kind of want to think of a fraction, but instead of this being a fraction of two numbers, we have a fraction of two polynomials. So m is a polynomial and n is a polynomial. And we set that the bottom cannot equal 0 because we can't divide by a 0. So remember, polynomials cannot have negative exponents, fractional exponents, or variable exponents. Okay, the numbers themselves can be negative exponent, but you can't have, for example, y equals x squared plus 2x to the minus 1. This is not possible because you can't have a variable to a negative exponent. So this is not possible. You could have x squared plus 2x to the 1/2. This is not possible because you have a fractional exponent, and we can't have x squared plus 2 to the x and have a variable in the exponent. Other than that, we've already sort of talked about what entails a polynomial. So with these rational functions, my top is going to be a polynomial and my bottom is going to be a polynomial. It could be linear, quadratic, cubic, quartic, or quintic, which are the main 5 polynomials we've covered in this course. They could give you anything beyond 5, but it kind of moves beyond the scope of a course. So when we deal with rational functions, the most basic rational function I could deal with is having just 1 over x. And this was a function that you guys dealt with in 20-1. So what you would have done in 20-1 is you would have looked the NPV of the function is what makes the bottom 0. And if I had x equals 0, that would be the value that makes the denominator 0. So that would be considered a non-permissible value. So at this value, when x is 0, which is a vertical line, there is a vertical asymptote at x equals 0. So therefore, my domain would be the set of all values from -infinity to 0, union 0 to infinity, but I'm not allowed to have 0 because I would be dividing by a 0 and that's not possible. My range, we'll do that after the graph is drawn and we'll work on that. So what I would just do to analyze this graph is just do a small table of values. We'll do a few positives and a few negatives. So when x is 3, y is equal to 1 over x. So I get 1 over -3, which is like -1/3. So 1, 2, 3, -1/3. When x is -2, I get 1 over -2, which is -1/2, which is smaller. When x is -1, my y is -1. We would have called that an invariant point in 20-1 because it's the same as the original function if I was looking at the linear. When x is +1, y is 1 over 1, which is 1. When x is 2, I get 1/2. When x is 3, I get 1/3. So these values are getting smaller. So when x is 1, y is 1. Then I go to 1/2. Then I go to 1/3, which is smaller. And you sort of see this kind of like 2-branch graph where the one branch has an asymptote going towards x equals 0, which is this line. And the other one has a branch that goes towards y equals 0, which is that line. Same thing on the other side. As x gets really large, my y's tend to 0. And as x gets really small, my y's tend to -infinity. So when I analyze a vertical line through the, a horizontal line through the function, I scan my function up and down. I see values in the negatives and I see values in the positives, but on the line y equals 0, there's no function. So my range would also be the same as my domain, which is literally y cannot equal 0. My vertical asymptote is x equals 0. My horizontal asymptote is y equals 0. And my end behavior. So this is the part that probably would be the most tricky to remember from 20-1. As x goes to infinity, y goes to, so as x gets really, really large, these y values are getting closer and closer to 0. Now, when we talk about getting large, we want to talk about getting large towards positive infinity and towards negative infinity. So as x gets closer to negative infinity, these y values will also look like they're approaching 0. Okay. The behavior around the NPV is also a skill you learned in 20-1. So in this case, my NPV is x equals 0. So I want to do as x approaches 0 from the left, my y value approaches, and I'll use a different color here. So as x is getting close to 0, what are happening to these y values? These are getting really large, but in the negative direction. As x is getting close to 0 from the right-hand side, this would be like what's happening to these y values. My y would be approaching positive infinity. So that would be my two statements that talk about the NPV behavior. And these two statements talk about the end behavior. So what's happening at the ends of the graph, the left end and the right end. Now, when you're dealing with rationals, this is again the most basic rational that you'll ever deal with. You kind of have to know this function cold. Everything we do will be compared to that function. So if we have transformations, we will compare it to 1 over x. If we have vertical stretches, horizontal stretches, reflections, or any of the other transformations we covered, this is sort of our main starting function that we would think of. Now, in general, when you're working through the rationals unit, we are going to ask you very specific characteristics all the time. So the first one would be your vertical asymptotes and your horizontal asymptotes. You need to include both. So my vertical asymptotes would take on the value x equals, and these would usually take on the NPVs. I'm just going to put them in quotations. It's usually going to be the NPVs, but not always. And your horizontal asymptotes will take on the form y equals, and then we'll have a number here, okay? We also want to consider something called a point of discontinuity, which is a new concept. And we'll talk about that as we move through the unit. So points of discontinuity. We would want to refer to our x and y intercepts of our graph. Is the graph crossing at the x-axis? Is the graph crossing at the y-axis? In our main rational graph above, we don't have an x-intercept and we don't have a y-intercept. Some people like to write that 0 with a line through it. We don't want to do that. If I ask you, you're just going to physically say no x-intercepts, no y-intercepts. Okay. Another characteristic that is important is your domain and range. So you want to make sure you're able to analyze that. The range is a trickier skill to do, so you want to make sure you're always looking at the graph when you're doing the range because it is very tricky. And we want to think about end behavior and behavior around the asymptote, which is our NPV behavior. So again, this skill I would consider high on the proficiency scale because this skill is challenging for a lot of people, even though it may not seem challenging, but it is, people struggle when it comes to the NPV behavior. So now what we're going to do is write some steps down, but basically when we want to analyze a rational function, so we want to look at what's happening on a rational function, And remember, a rational function is a function that has a polynomial divided by a polynomial for my formula. And the top polynomial and the bottom polynomial can be completely different, okay? Basically, you need to factor the polynomials. So that's the unit we just covered. If you have a quadratic, you would factor it using your grade 11 skills. If you have a cubic, a quartic, or a quintic, which is your degree 3, 4, and 5, you would have to use your factor theorem, remainder theorem to guess a root, and then go from there to continue with factoring it. So basically the zeros, another word for zeros are x-intercepts or roots, of the denominator these form our non-permissible values, and they're going to be all of the NPVs for the problem, okay? The zeros, so common factors, I'm just going to write it like this, common factors, they turn into PODs, okay? So I'm going to call the POD a point of discontinuity. You can call it a POD, POD. So I'm going to abbreviate that. These will turn into our PODs. I'm just going to write the zeros of the denominator that are not common factors. And I'll explain this a lot more when we do an example. These will turn into your vertical asymptotes of the function. Okay. Now the zeros of the numerator, which are not common with the denominator, these turn into our x-intercepts. Okay. And to determine the horizontal asymptote, you need to look at the degrees of the function. So I'm going to say horizontal asymptotes determined by degree of top related to bottom. Okay, so horizontal asymptotes, I'm going to give you some rules. Basically, you're going to look at the degree of the top, which is the exponent that has the highest power on the variable. And then we're going to look at the degree of the bottom, and we're going to do some relationships with that. And then we're going to use, and then NPV behavior and end behavior, we're going to look at the graph to determine that. I'm just going to kind of put a note, we're going to look at the graph. So this little box that I just wrote down, filled with information, it's sort of the summary of all the stuff you should be picking up as we do questions step by step. And if you're learning the questions step by step, then basically these are the things that will summarize all the skills you need in the section. So we're going to go through some examples to help us determine all of these characteristics in a given problem. So what I want to do first is I want to look at my polynomial function, which is given by the stuff in green. And I want to see this is a rational function. How do I know that this is a rational function? They give me a quadratic polynomial on the numerator because I see a power 2, so degree 2. And I see a quadratic polynomial on the bottom. So first step we're going to do is factor the top, factor the bottom. So we need two numbers to multiply to -4, the same two numbers to add to -3. You go through your process either using the swing method or the decomp or whatever you learned in 30-1. I'm going to figure out my numbers to be -4 and 1. And when you end up factoring that, you're going to get x minus 4, x plus 1 because my a value is 1. My denominator will factor into x minus 1 and x plus 1. So at this point, before I do anything, the first thing I want to do is I want to state my NPVs which are all the things on the denominator that make it 0. So what makes that bracket 0 would be x equals 1. I'm going to write the NPVs as restrictions, so x is not allowed to equal 1. And from this bracket, x is not allowed to equal minus 1. Those are NPVs. This automatically forms my domain, which is the set of all x such that x cannot equal plus or minus 1, and then x can be any real number. So I'm good with the domain. We figured out the domain, and we figured out the NPVs right from the start. Now what we want to look at is anything that's in common. So this is a common bracket on top and bottom, so those will cancel out. So what that means is the common factors turn into the PODs. So my common factor was x plus 1. So that means at x equals minus 1, I have a POD. So that means at minus 1, comma, and we're going to figure out this point here as an ordered pair, there is no graph happening. The graph doesn't exist, and this causes a point of discontinuity, which is a hole in the graph. Okay, we're going to find that y-coordinate, but we're not going to do it yet. So I'm going to take my simplified expression, and I'm going to write it below here. So my simplified expression is x minus 4 over x minus 1. And I'm going to state that x is not allowed to equal negative 1 because that's the common factor that had canceled out. Okay? Now, if I take negative 1 and sub it in there, I get negative 1 minus 4 over negative 1 minus 1, which gives me negative 5 over negative 2, which is 2.5. That would be the y-coordinate of my POD, and to figure it out, I just sub in the x-coordinate into my simplified expression. If I try to sub minus 1 into this expression, I'm just going to get a 0 over 0, which is really weird, and you've never seen that before. So you got to really watch if you get something weird happening. Now, we've stated the PODs, even though the question didn't ask us, but we want the equation of the vertical asymptote. So basically, the factor that didn't cancel out is this piece, and that piece turns into my vertical asymptote. So my vertical asymptote is at x equals positive 1, and it's coming from that factor that didn't cancel out. Now, I also want to look at the numerator in its simplified form, and that value on the numerator in simplified form forms my x-intercept. So this is in a factored form, so my x-intercept would be positive 4 and 0, and I don't even have to algebraically do it. This is what it would work out to. If I sub in 0 for y, I multiply both sides by x minus 1, and then I solve for x, and I'm going to get 4. So there's my vertical asymptote. We need to do end behavior and range. So for right now, what we're going to do is we're going to do the graph on Desmos to be able to come up with the domain or with the range and with the, what else didn't I find? The end behavior. Okay, so NPV behavior, end behavior. So in order to do these, we have to look at the graph. I think it's the best thing to do is look at the graph. So I'm going to go ahead and I'm going to graph this function. I'm going to put on all the information I know already. So I have a vertical asymptote at x equals 1. Okay, and then I'm going to label my graph x equals 1. I have an x-intercept at positive 4, so 2, 3, 4. That I'm going to label that point 4 and 0. I have a POD at negative 1 and 2.5. 1, 2, 3. So I'm going to put an open circle there because there's a hole in the graph. And that's pretty much the main information I have. So what I'm going to do now is I'm going to go to my Desmos and I'm going to plot x minus 4 over x minus 1. So let's go ahead and look at what that graph looks like. X minus 4 divide by x minus 1. So I'm basically looking at this to determine what the shape of my graph is going to look like, so I can scribble it into the sketch I already have. And I will get this graph right here, but you're not going to see the POD showing up at -1 because I didn't put the non-simplified form of the equation in. So I'm going to come back over here and I'm just going to draw the graph that I sort of saw. And so the graph I sort of saw was a graph that went through my POD and then it gets towards my vertical asymptote. And then this side is going to go towards my, it's going to go towards my vertical asymptote on this side. And then it's going to kind of level out somewhere as a horizontal asymptote. So what we're going to do is we're going to look at the degree of the top and the degree of the bottom. And because these degrees are the same, I'm going to take the leading coefficient of the top and the leading coefficient of the bottom, and that would actually happen to be the location of my horizontal asymptote, which in this case is y equals 1. So this graph will have an imaginary horizontal line at y equals 1, and then basically the graph will level out at that point. So my range is going to be the set of y such that y is not allowed to equal this whole, which is 2.5, and also y cannot equal positive 1, because that's the location of my horizontal asymptote. And other than that, if I were to scan the function up and down, it hits every other x or every other y value in this graph. My NPV behavior, actually what we're going to do is leave this for a moment. I'm going to just say leave aside for right now, and we're going to come back to that. And the end behavior, we can do this one. So this one is as x approaches infinity, what's happening to my y value? So as x gets really large, that y value will look like it's approaching 1. Now I'm going to do the other side. As x gets really large on the negative side, my y is going to approach. I go towards the negative infinity side. This is going to also approach 1, which is usually the value of my horizontal asymptote. Okay? Now, with the NPVs, the reason I wanted to leave it aside is A, I wouldn't have had room to write it in that small space, because how many NPVs do we have? We have an NPV at 1 and at -1, and they're both doing different things. So I'm going to come aside and pull that NPV behavior all the way up here, and we're going to cover it here. So as x approaches, let's use the -1 first. From the right, y approaches. So what I'm going to do is I'm going to use another color. So I'm going to approach my POD from the right-hand side, and as I'm approaching -1 from the right, it looks like I'm going to go to the hole, and the hole is located at 2.5. As x approaches -1 from the left, my y value is going to do pretty much the same thing. I'm going to come this way, and as I get really, really close to that -1, my y value is going towards that hole, which has a y coordinate of 2.5. Now we're going to do the other NPV, which is +1. As x approaches 1 from the right, my y approaches, so I'm going to use another color. So as x approaches 1 from the right, which means I'm coming towards this vertical asymptote, my y is approaching -infinity because my graph is going down. I need to do the NPV behavior from the other side. As x approaches 1 from the left, I'm going to look at what's happening to my graph as I approach 1. That piece of the graph is heading up, which means my y's are going to plus infinity. So basically, this one example I did with you guys will cover all of the different types of examples that you will need to cover, except now they're just going to vary with different numbers, different polynomials, different degrees, and so forth. So we're going to keep working through these examples, but we're going to do them quite slowly so you can sort of get used to the process. Now, basically, I want to teach you how to find the horizontal asymptote. So in order to find the horizontal asymptote, you need to compare the degrees of the polynomials. So if the degree of the polynomial is higher on, well, let's start with the same degree. So if both polynomials are the same degree, so both polynomials are the same degree, basically what we're going to do is we're going to divide the coefficients of the highest degree terms. So you look at the leading coefficient on the top, the leading coefficient on the bottom, and that value would give you the horizontal asymptote. So just like I took leading coefficient, the x squareds both had a coefficient of 1, and 1 divided by 1 is 1, so my horizontal asymptote was 1, okay? So one of the major categories, polynomials are the same degree. If the degree of my polynomial on the numerator is lower than the denominator, so if I'm going to say if degree of top is smaller than degree of bottom, then we have a horizontal asymptote at y equals 0. Okay? And if the degree of the numerator, so if degree of top is bigger than degree of bottom, okay, we say that there's no horizontal asymptotes. But sometimes what can happen is you'll get a diagonal asymptote. So in a given question, you'll get diagonal asymptotes and you need to know that they are there, but you don't need to know how to find them, okay? So let's work through. So I'm going to say degree top is equal to degree bottom. We have y equals leading coefficient of top divided by leading coefficient of bottom. Okay, that's kind of the big rule. If the degree of the top is greater than the degree of the bottom, there's no horizontal asymptote. And then if degree of top is less than degree of bottom, we have y equals 0. So these are your three main rules relating to horizontal asymptotes. Okay, so example 2. Determine the horizontal asymptote for each function. So what we're going to do is degree of the top is what? We look at it, we say, oh, this is a linear function. My highest power on the variable is a 1. So the degree of the top is 1. The degree of the bottom is also 1. So the degrees are the same. So my horizontal asymptote is at the value of the leading coefficient on the numerator is the 4, and the leading coefficient on the denominator is the number in front of the x, which is an imaginary 1. So 4 divided by 1 is 4, so that would be the location of my horizontal asymptote. We look at the next example. So the degree of the top is 2, degree of bottom is also 2. So they're the same. So I take my horizontal asymptote would be the value of the leading coefficient on the top divided by the leading coefficient on the bottom, which is 3 and a 1. So therefore, my horizontal asymptote is at y equals 3. Let's take a look at the next example. the degree of my top is 1 because I have a linear. The degree of the bottom is 2. So my degree of the top is lower than the degree of the bottom. So we fall under the category where y equals 0 forms our horizontal asymptote. Okay. And then finally, the last example, the degree of the top is 3. The degree of the bottom is 2. So the degree of the top is higher than the bottom. So there's no horizontal asymptote. But make sure you consider a slant asymptote or like a diagonal asymptote because the degree of the top is 1 higher than the bottom. So the slant asymptote is kind of forming because the top is higher than the bottom, and the top is higher than the bottom by +1. So that's what's causing the diagonal asymptote, is that the bottom has 1 less degree than the top. Okay? Now we're going to do this example with everything all over again. So we have our function. Okay. Now remember, we're going to try to remember the steps. The first step is to factor and identify the NPVs. So again, you want to go ahead and remember your grade 11 factoring. 2 numbers need to multiply to -6 and add to -1 for my denominator term. Okay, you're going to go ahead and factor that. So I'll give you a minute to try that, and I'll just pause here for a second. When you complete factoring this, you need to consider your 2 numbers that caused you the -6 and the +1, and it looks like it would be a -3 and a +2. So I get x minus 3 and x plus 2 for my denominator, and my numerator is already linear, so I don't have to worry. I'm going to state my NPVs, which is x cannot equal the value that makes that one 0 is x equals 3. And the value that makes this bracket 0 is -2. So those are like the zeros of my denominator. So x cannot equal 3 and -2. Step 2 would be to write out domain, because the NPVs directly make up your domain. So my domain would be the set of values. So I'm just going to kind of draw you a number line. So we're not allowed -2 and we're not allowed 3. So I'm allowed any value between -infinity and -2. I'm going to put a union sign because I have more than one bracket included. I'm allowed to have any value between -2 and 3. And then on top of it, I'm allowed to have any value between 3 and infinity. So that would be my domain in interval notation. Okay. Step 3 is to look for PODs. What you want to do when you're determining PODs is look for cancellation. So in my example, there was no cancellation. So this means no PODs. Nothing canceled, so I can't have a point of discontinuity. Step 4 is to identify your vertical asymptotes, which are coming from the non-canceled terms. So I'm going to look at the terms remaining on denominator after cancellation. Okay, so the terms that remain on my denominator are the 3 and the 2, or like the x minus 3 and the x plus 2. So that's leading me to having a vertical asymptote at x equals 3 and a vertical asymptote, and I'll maybe just write it in one sentence here. So it's going to be x equals 3 and x equals minus 2. So this graph has two vertical asymptotes. So what I'm going to do is I'm going to start a running sketch of the graph on the right-hand side, or the left-hand side. At x equals 3, there is a vertical asymptote. So this is x equals 3. At x equals minus 2, let's say that's about there. There's a vertical asymptote. So far that's what we know. Now, what we would do is step 5 is to look at the x-intercepts, which is looking at the numerator for things that are remaining after any cancellation. So we're going to look at the numerator. So I'm going to say, look, whoops, I don't want to write with highlighter. Look at numerator. After any cancellation. Okay, in my case, I'm left with an x minus 1, which means my x-intercepts form at positive 1 and 0. So I'm going to go ahead on my graph, 1, 2, 3, 1, 2. I'm going to make an x-intercept at 1, 0. Now basically on my graph, I've included any information I'm able to include by doing it by hand. So now it comes to the calculator. Ooh, wait, we need to do horizontal asymptotes next. Forgot about that. Let's look at the degree of the top. Is it bigger or smaller? So my degree of the top is power 1. My degree of the bottom is like quadratic, so power 2. So my degree of the top is smaller than my degree of the bottom. So you have to remember, what condition does that cause for horizontal asymptotes? It causes this condition right here where degree of top is less than the bottom. So y equals 0 is my horizontal asymptote here. So I'm going to come in, I'm going to draw a dotted line at y equals 0. And then literally I should know what my graph looks like. Now the weird thing is I have a horizontal asymptote. I'm going to erase it for a moment. Whoops, I didn't want to do that. Whoops. Okay, so I'm going to leave it in there, but you're going to notice the graph is crossing at a horizontal asymptote, and that's okay. The graph is allowed to cross at a horizontal asymptote, but it cannot cross through a vertical asymptote. So once we get these 6 steps done, we're just going to go into our calculator and type in the remainder of the function. And the only way you would know what the behavior looks like is to actually draw the graph with the aid of your calculator. So x minus 1, x minus 3, and x plus 2. So I'm going to get an x minus 1, x minus 3, and I think I've already forgot what the function's supposed to look like. And then I have a x minus 2, and I have to double check because I've already forgotten. So x minus 3 and x plus 2 on the bottom. X minus 3, x plus 2 on the bottom. And then my numerator had an x minus 1. So what I'm literally going to do is I'm going to remember the shape of this. And basically, I'm just going to draw the shape of this into the graph that I've already made. So this graph is going to sort of do a slide down through there like that. And then when I look at the branches, the first one is on the top and the second one is on the bottom. So this one would kind of come this way, make it go through my, towards my horizontal and towards my vertical asymptote. This one is going to come this way and down towards my vertical and horizontal asymptote, and that's my graph. Now, once your graph is drawn, then we're going to look at the range and the end behavior. So let's look at the range first. when I scan my function up and down, my graph, it looks like it doesn't cross at the horizontal asymptote, but if I look at this middle branch, it actually crosses everywhere. So my range is actually YER. And it's really weird, but it is. This is weird for people because they see a horizontal asymptote, but the graph is crossing through that horizontal asymptote, and that's okay. Let's look at my end behavior. So this is talking about the ends of the graph. So as x gets really large this way and really large this way, what's happening to my y value? Whoops, we're not in calculus yet. As x approaches infinity, y approaches. So this arrow is going to go down and down and down towards my horizontal asymptote. As x approaches negative infinity, my y is going to go up, 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 up towards my horizontal asymptote, which is 0. This is just confirming that our horizontal asymptote is at y equals 0. So that's a good sign that that went to 0. Now we're going to do behavior around the NPVs. And we have 2 NPVs, so I need 4 statements, 2 for each. So x equals minus 2. So we need to do as x approaches minus 2 from the left, as x approaches minus 2 from the right. What's happening to my y coordinates? So let's look at the graph. As x approaches 2 from the left, I'm on the left side, this is going down and this one is going up. So the left side is going down to minus infinity, and the right side is going up to positive infinity. Now my other NPV was 3, so as x approaches 3 from the left, my y approaches something. As x approaches 3 from the right, my y approaches something. So let's pay attention to that. I'll use pink. So as x approaches 3, this piece on the left side is going down to minus infinity, and this piece on the right side is going up to plus infinity. So the left side is negative infinity, the right side is plus infinity. My end behavior is done. So my suggestion to you is to give yourself examples where you have polynomials divide by polynomials and work out all this information, draw the graph. Work out the information, draw the graph, find all the characteristics, because this is primarily what analyzing these graphs is going to look like. Very cumbersome, very long process. Now with this example, they give you a graph and you need to decide what does the equation look like. So now I'm taking all of this information from my graph and working backwards to get all the information out. So let's start with our key points. There's a POD at this coordinate and that coordinate, which is at positive 1 and 2. How do I know that's a POD? Because the graph shows me that there's a hole right there. I have a horizontal asymptote at this value, and if you follow my scale, that's a value of y equals 3. I have a vertical asymptote right there, which is at x equals 4. And this is all one more piece of information I need, which is my x-intercept. And this is kind of the key information I need to start making an equation for my graph. So my x-intercept is right there, and if you follow the scale, that's positive 3 and 0. Now with all of this information, we should be able to come up with a function. Now you have to remember the POD means that there was cancellation. And with the vertical asymptote, it shows up on the denominator. Cancellation means it showed up on the numerator and denominator. If it's an x-intercept, it shows up in the numerator. And then we'll talk about the horizontal asymptote in a moment. So what we're going to do is, because the x-coordinate of my POD is x equals 1, we're going to convert that to make it look like a factor. And because it's a POD, we know that there had to be an x minus 1 on the bottom and an x minus 1 on the top, because they would have had to cancel out in order for me to get that POD in my graph. Now, because I have a denominator of 4, if I turn that into a factor, this would become x minus 4, which is telling me that I have an x minus 4 factor on the bottom that doesn't cancel out with anything on the top. This one, x-intercept, is telling me I have an x minus 3 factor that didn't cancel out on the top, which is producing a x-intercept of positive 3. And then basically when I write all this information in here, I get a quadratic on the top and a quadratic on the bottom, and they both have a leading coefficient. So when I'm looking at the leading coefficient, 1 times 1 is 1. So when I distribute that out, I would get a positive x squared. And then when I distribute this with this, I would also get a positive x squared. So the leading coefficient of the top is a 1, and the leading coefficient of the bottom is a 1. But this is telling me that I have a leading coefficient of the top being a 3, the leading coefficient of the bottom being a 1, because I need to get a ratio of 3 over 1. So I'm going to put the 3 out here and the 1 out here. And this should be the equation of my graph, and you would probably want to use a point to check it. So you want to find a point that lines up exactly, and this one may look like a good point. So that point looks like it's at 7 and 4. Let's double check. You know, sometimes you may not be able to check your answer depending on, you know, if they give you all the right information. But when I sub in x is 7, my y answer should be 4. So I'm going to sub in x is 7. Sub in x is 7. So 7 minus 1, 7 minus 3. Sub in 7 minus 1, 7 minus 4. And I'm expecting this to be a 4 because I want my y coordinate to be a 4. So this is 3 times 6 times 4 divided by 1 times 6 times 3. So you're going to notice that there's a 6 on the top, 6 on the bottom, they cancel. 3 on the top, 3 on the bottom, they cancel. And I'm left with a 4, so left side equals right side. So this checks out that this should be my correct equation for that graph shown below. Okay? As always, practice this, and if you have any questions, feel free to email me, but we will do a little bit of review on this when I come back to class, or at least an exit slip or something to make sure you've picked up the ideas. But again, this is quite a cumbersome unit, so if you're not practicing, you're going to forget the skills of how to find each of the pieces of information given in each example. Okay? Have fun, and we will chat again soon.